Hello, welcome back to the stream. I'm Jun-chan, and today we're doing some more graph-related things. Actually, we're getting back to writing Comonads. We were implementing a number of missing sort of high-level modules from our port of the algebraic graph library or ALGA from Haskell to Purescript. And that's the non-empty graph type. And having a non-empty graph type should allow us to go back to implementing Comonads and have the necessary tooling to do that. So I suppose I should do my usual housekeeping. So we are the 26th, and the log is here. Okay, so let's see. Alga here. Yeah, we had checked that our test still ran with a few moves in the module structure, but that's obviously a good start. And then, yeah, I left some breadcrumbs here and there to, for instance, do a non-empty undirected graph and something that doesn't exist in Alga actually, in the original library. But we are going to focus on Comonads today. So let's see. So the way I was starting to work on this was by implementing this focus graph data type, which is a little bit of an analog to using to a list zipper being an index on the list and the list itself. So it's just a way to say, well, if we know which node we're pointing to and that we have the structure of the graph, then we have enough information to make a comonad out of it. So especially if we have a non-empty graph, right? So I think I'm going to continue a little bit with that, but there's another representation to look at, which is this one that Paolo, my friend Paolo, came up with, which would be a way to keep track of keep pointing to the place where we have our P vertex, which is our selected vertex. And I'm sure all of these representations will, and we have another representation lower, I think, pointed graph. I think haven't I started a context graph, right? That's another one. And I'm sure all of these representation will in fact behave differently depending on what we want to do with the comonads. In particular, in changing focus, for instance, inside the graph, that's going to be different. So changing focus in a graph that's indexed like that is going to be a little bit costly. It's going to mean rearranging how, basically probably having to unfold the data structure and then repackage it. Here, on the other hand, it's really simple. We have to move from one key to the next. But on the other hand, we have to worry about out-of-bound errors here. So the interesting thing with this representation is that it keeps this sort of like invariant that Alga has, which is that all our graphs are correct by construction. So, and then apart from just pointing to a key, there's this other representation, which I call context graph here, which would extract a context, or here a context prime, which includes the vertex that we're focusing on. So it's, in this sense, it's, I mean, with only the vertex, it would be isomorphic to my focus graph. My focus graph here, the key being the vertex here, or the A that's being passed. But the other things that we can find in the context graph here are incoming edges and outgoing edges, or inputs or outputs, which are lists of vertices from which edges are coming from. And this decomposition here is closer to the decomposition that is mentioned in this blog post, which in fact really, I realized later, is a port of the Haskell FGL library. And maybe I should go to Hackage. And I read the paper a while back. I haven't reread it recently, but I think it's part of the trick that allows to make this data structure inductive, is that you can pattern match on a node, but you need to pattern match on all of the existing edges from that node in order to be able to, I suppose, refer to the complement of it. Would that be? I mean, or I suppose in the inductive, with inductive reasoning, it would be that those are that's the data structure that you would need at each step in order to build further the rest of your graph. So, and then the pattern matching would also mean that you can determine the thing that is matched and the rest. So a little bit like a list. And so that's also the intent, the ability to do pattern matching and use these functional idioms is also the intent with Alga. So, but in Alga, actually, that would be an interesting thing to do. And I suppose that this relates to what I wrote here, right? Which is we're wondering whether whether we use focus graph or pointed graphs or context, what I call context graphs. This is something I invented. That I haven't seen that name used elsewhere. I propose to work on undirected, and then work on the Comonad for these undirected graphs. And find out if context is needed. That is a little bit, I think, what I'm asking here. And yes, maybe that's right. Then look into labeled graph maybe later. So I suppose it's about finding out more about context. I mean, I could write a Comonad for focus graph. I mean, I already have a Comonad for focus graph. So we should maybe check on that's the other way around. On our Comonad for focus graph, make sure that it works, and yeah, move forward from here. So pointed or focus graph has the key. Extract is just the key. Calling it key is a bit misleading. I think maybe I should call it V because it's really the type of the vertex. But to be honest, I don't like the term vertex for a node. It's a little bit confusing to me. I think I prefer using node. So it will be a N, and I'm going to do the same thing here, and that would be N, 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 N. So when we pattern match on a node, we get back the node, and that's the extract. And we ignore the rest of the graph. So here we see that there's just this this thought that came into my mind, which is what I was saying earlier about this idea of pattern matching and having the thing that we match on and also the rest, right? And that being an objective that both FGL and Alga were pursuing. And now I'm realizing that just the Comonad structure doesn't give you that. And I wonder whether that's related to strength, because this appears in perfunctors. and therefore I wonder whether it relates to length, and I wonder what it would mean to somehow have also being able to extract but also have access to the rest, the thing that hasn't been extracted. And that relates a bit, I'm jumping a little bit ahead in my about this context and the representation of context, and whether graph includes that context or it's the graph without the context. But let's see. So FG is shadowed apparently, so that's because we have duplicate FG here. Yes, so let's say FG prime and FG prime, and I think I already have some tests for this, to be honest. Yes, so let's go check out the tests. It's for what we call focus graph, Comonad focus graph, extract from the Comonad, the focus graph Comonad, and so I'm using the Comonad over booleans as the node type. So there's only really two possible nodes, and I create the non-empty graph. Oh, I call it non-empty graph here. That's problematic. So hold on. Non-empty edge. Oh, oopsie. Edge. Right. Yeah, so this is the edge for non-empty graph, and then my focus graph is a wrapper around that. So I don't yet have this more classy interface to refer to all graphs. I've started working on it. I think as I start to multiply the instances of graph that are of interest, this is going to become more and more confusing. So maybe I won't do it for focus graph, but as I start with context graphs or whatever that is, I'm going to try and regularize the API and use a classy approach for that. I actually already started to do some tests for the class version of things, the classy version of things. But I haven't done it for the any graph yet. Yeah. So, okay. So I can make a simple focus graph. I think that's fine, but let's put it underneath because I have Comonad focus graph underneath as well. So it makes sense to have this here, I think. And so if I extract, and this is really already Comonad focus graph, to be honest. It's I make the simple graph, but I'm extracting here. So oh, but this is the same. Okay, I see. So this must have been me trying to, I mean, making a placeholder. So maybe it's not about extracting, but then I suppose we don't really have interesting primitives to build a focus graph or to unfold the focus graph. There's really not much to test here, is basically what I'm trying to say. So let's just remove that. And let's see. So duplicate, so extracts true, that's really simple. Duplicate, how do we test this? We extract twice and see that we get true. Right, and then I'm also testing refocusing. so that if I duplicate this same true-false graph, and then I refocus on the focus graph false, since duplicating is going to mean that the key is going to contain a whole graph in it. So I'm refocusing on that key that is the whole graph. And then since refocus gives us a maybe, we extract the maybe, we unwrap the maybe and then extract, and we're hoping to get into false, whereas here we're getting true from the extract because we've now refocused to the false node in the graph of graphs. This is all very inconvenient, and what I would like is to be able to specify how I move inside the graph, as opposed to refocusing on an arbitrary node. It's particularly bothersome when with this formulation where I have to refocus passing like a whole key as a graph. So the thing though is that in this focus graph formulation with only a key here, I suppose we don't have really readily contextual information to know whether to know which edges to follow. So we would have to do quite a bit in order to implement a move along the edge notion, whereas it would be very natural to do with the context graph expression or formulation. And right, if I try to focus on something that doesn't exist, then refocus should return a nothing, I suppose, a true equal true, and this should not fire. This is, of course, this is an ugly. I will become better at testing in Haskell or in Purescript. Okay, so I suppose let's go for context graph. I think this is as much as we can do for Comonads for focus graphs. And we already listed it here. And so, yeah, indeed, we do find that context might be needed for move. So maybe we'll write this here. Seems useful for implementing moving along an edge. And then it would be also useful for unpacking a product. Between some focus and the rest. With the question, is that some addition, some strong structure added, Comonads. It's most certainly not that, but I think that there must be a relationship between the I don't even know how to say this, But this makes me think about, is it lenses over T, or I'm not sure whether that's it. It might be it. You know what? Maybe not. Lenses, prisms. I think it's actually from backpack. Let's call it backpack. Who writes this? Edward Yang. Easy Yang. That's the one. Except that's a tech file, okay. Okay. That is really? Did we have a date? We did not. Yeah. Ah, okay. Lenses. Except no. Did this go away? Prisms. They might have gone away. Card.org. Embody. No. How strange. How strange. And annoying. There we go. This idea that every product yields lenses, and every sum yields a prism, being the dual of that. And prism or not. And the perfunctor lens, AQ. the lens, we're saying that S is isomorphic to AQ. That means that we have at our disposal some PAQ for a monomorphic lens or non-type changing lens. And yeah, take a relationship on A, since its relationship on AQ, and ignore the Q. It happens to be a type class called strong that gives us just that. So that's in that sense that I mean strong, but strong is for profunctors. So is there some comonadic structure for perfunctory structure with comonads? Comonad profunctor. In interest there is, or something. Why would comonad be underneath profunctor in the type hierarchy? That's already interesting. So Idris comonad. Oh, so there's a control comonad, but there's also a data perfunctor comonad. Okay, so that's strange. Okay, so there's this one. That's from recursion schemes. Data perfunctor. It sounds like maybe it's a bit of an isolated thing. Plus, we're not sure, in the absence of a package repository here, we're not sure what's going on. So wouldn't mind going to the GitHub, to the source for this. So I suppose that's recursion scheme VM Chalet. Interesting that it's in recursion schemes, by the way, and not even a data perfunctor right there. Strangeness. And yeah, it's a bit of a one-off structure there, and it's not clear why it's in data perfunctor. So it could be completely arbitrary, or it could be some deep insight that might or might not be documented. Let's see, Erba, monadic versions. I could be related to the, since it's recursion schemes, it could be related to the recursion scheme with comonad approach, but that recursion scheme with comonad approach, I don't remember it mentioning full functors, recursion with comonads. And that's one of the things. So we could, I suppose, look at the PDF and then the blog posts. Was there perfunctors here? There weren't. And here we're not gonna know, I think, because we can't search very well through PDFs. But maybe here we can. It seems like we can, but there's no perfunctor quoted here. So this is a bit strange, to say the least. And okay, well, let's look at the structure. Well, it doesn't. There's only functor. Coffee comonads useful for isomorphism and recursion. That sounds fine. And then there's a comonad co-free type class, I suppose, interface, and the constructor for co-free comonad. But nothing seems perfunctory here. Yeah, that's just how to construct a co-free from a generator. And I look at it and I see a mealy machine, by the way, but I look at this some other time. So perfunctor and comonads, yes or no? Is that a thing? Is that not a thing? Perfunctor comonad. Defines a pro extract which returns I have no idea how to read this. But if it's here, it needs to be in Haskell. I mean, and well, it's not in data perfunctor. I mean, it's possible that it's in Scala and not in Haskell. That would be a rare thing, but I suppose it's possible. And Purescript perfunctor. How about that? Given there's a few things that reflect on costar f. With f being a comonad. Turns a functor into a perfunctor backwards. Ah, right, okay. Yeah, that looks like a comonadic extract right there. I wonder what that means. Star gives a monad. It also gives a category if f is a monad. It turns a functor into perfunctor. And what, you give it the functor and then it's done. Star f is the Cleasley category for f. Yeah, I'm not sure this is in the right direction that I see. Thinking this is where, if you see the comonad, the comonad is some kind of context, and then you can extract a single value from it. I think the profunctor structure is going to allow to work on the input and outputs of these two, of the two ends of these arrows. But I don't think that that's where that kind of focus and rest structure is. So maybe there's another profunctor that looks at that structure from another endpoint. An idempotent profunctor comonad on C in Sketches of an Elephant, which I think is a very well-known book. Local compactness for any continuous category. Since profunctor composition, comonad. Exponential toposes, huh? Wow, so above my pay grade, it's not even funny. Okay, so if it is some kind of strong structure added to Comonad, then really we don't know. But I said I would do some Comonads, so let's. And so I suppose we could do it with pointed graphs, but I think we really need to do it with context graphs, because pointed is more of an oddity, I think, in my view for now. Okay, so I think I did say that I would actually use more of a class machinery for this, but maybe what I should do instead is create a, or first maybe, is create a non-empty context graphs here. Module, and move some of my non-empty stuff there. That would be, I think, a good first move. And let's take all that stuff. And then here we can module algebra.graph non-empty dot context graph where. And so I suppose we could now call this context, which is one of the niceties here. And then what? Then we want to import a number of things. I suppose we'll need to import most of this, as well as the internal to get the list. And then more pedestrian things. So maybe we'll put them first, after that maybe, and the prelude. Right, but then some stuff would be coming from, I thought this would be in algebra graph non-empty, but no. This is in, I thought this was in internal, to be honest. Focus, right? There's a bunch of focus related things here, but I think it's just that it's that one, yeah, focus on a specified subgraph. Okay, this doesn't compile anymore. Because we don't have, there's a bunch of stuff we don't have anymore. We don't have context prime in particular. But we still have focus graphs. Yes. And I don't know whether we should have them, to be honest, meaning we should have them here. I think we should have them probably in non-empty context graph or focus graph. But so focus is not exported then from non-empty, so that's not the best. it's using context. And we have a refocus as well. Yeah, let's export it. And now we have it, and we want to import data.array as array, and we want to switch to context here, and we type check now. Okay. So decompose and so on, I think, is trying to find inspiration from Purescript FGL, which we sort of implemented very mechanically when we added this pointed graph type, and we called it pointed graph here, and it's the version that has a context, and the context, where is the context defined? It's defined in inductive types, and right, it has this incoming node and the label as well, and the outgoing. And yeah, decompose is indeed an attempt to create a graph decomposition, and a graph decomposition is again a type that is a decomp rec, which is a context and a remaining. So again, we have this structure, and that one's lazy. Trying to remember how I figured that out, because I remember, well, we did this pointed graph submission. I actually followed the implementation from someone else, and yeah, well, it actually doesn't matter so much. Oh, it could be that just decomp, this was already existing. This had been done in the Purescript FGL library before I did anything. And I think that's most probably the case. And what am I looking for? Types. And yes, exactly. It was done properly by Alex, I suppose, who's done this library. I don't know who Alex is, by the way. Alex Hubert. Okay. So decomposition seems to be key in how we were doing this Comonad. Specifically extend, I think used it. Yes, decompose right there. So, and then from decomp, I should wrap, word wrap here. This is hard to read. So decompose takes a pointed graph and separates it into its context and a remaining, which is lazy. But in this case, we just mechanically construct it. Extending is about casing on the outcome of a match any done on that extent prime. And that extent prime takes a pointed graph, a function from a pointed graph to a v, a regular graph, and outputs the regular graph. And when we do decompose and from decomp, I don't even know what merge is. What is merge? Merge is the way to union two graphs. Oh, no, it's a way to merge a context into a graph. With some invariant there. I'm now thinking about monoids and cancellative monoids and comonads. I mean, this is obviously not a graph, but it's close. It's close to being a graph. You could even look at this as a kind of update monad, actually, right? Like this being an action or an increment, a delta being added to sort of a set action or monoid action or something, like a graph action. Although we don't have a concept of removing things. Okay, and so that was merge, and so we unquery merge, I suppose, means that we're able to apply it to that context. So we've decomposed now our pointed graph. But what a strange thing to do. The pointed graph, doesn't the pointed graph contain the contexts? Here? We have a context C here. Why do we decompose and remerge? We could just merge C and this. It does not make a lot of sense. Did I add test to this? Pointed graph, should we focus a pointed graph Comonad? So I did, or maybe I didn't. Maybe those were here before. They probably were. Maybe not. Okay, so of course, if I get inspiration from that, from the way that this is written, then then I need to make sure that it's actually as simple as it could be. But to be honest, I don't even, this is weird already, like this, the way to decompose, but I haven't even really grokked how the algorithm worked either. So match any, what does this do? Match any decomposes a graph into context for an arbitrarily chosen node and the remaining graph. Oh, right. So that's the pattern matching. That's the use of the inductive decomposition. And match any is basically doing a decomposition that is arbitrary. And so I think the assumption would be that it would be fast, maybe. Oh yeah, I did put this as a draft. So that will be very different for Alga, of course. But the idea, therefore, with match any is that we can decompose the graph. And so when we case on it and that we get a decomposition, then I suppose here we have a chance to recurse. In this case, we refocus but that's it. The question is, when do we apply the F? And the answer is during the extend prime. That's where we change the label. Apply the F. By the way, the F is a function from the node type. So it's only a node relabeling, right? The question of node relabeling versus edge relabeling is going to be interesting. And because this might be another indexed Comonad structure. Don't know, maybe. So let's look at it again. Given a whole F and the graph, we decompose the graph into a context and a remaining, and we apply F to the node. That's the refocused, the whole refocused on the context. Yeah, because we're decomposing it. So this is wherever we were at. And we apply F to that. And the context, we map context for that. Which is that we make sure we pass a new context in which the label is also modified. The label is new label. Okay, yeah, all right. So we extract the value from the context, we apply F, and then we repackage that into a new context, and then we merge the new context with the graph, and with the graph and with the rest of the graph being recursed upon with that extend prime. Okay, yeah, I think it's a lot of extraneous work there to actually do this. I wonder whether I can rewrite something that's easier here. but I think I'll do it with alga. And so the idea here given a context graph, extend, we could write as extend, we could write it as duplicate. Maybe I should try and write it first as extend. Extend would be of type WA to WA to B. No, it's actually A to WB to WA to WB, isn't it? We need to import Comonads. And then we'll want the type for extend. WA to B, WA to WB. Yes. Okay. So RFG is going to be something that we can actually pattern match upon, right? Which is either a vertex or connect or an overlay. Except not, because we have the context in tow. So it really is context graph of a context and that vertex. Hence case, because I think case is in fact much easier to write, because we don't need these parents. Okay. And okay. So if we have a vertex, then we apply F to A, and then what do? We need to repackage a WB. So we return that. That's a B, or no, yeah, no, that's a WB actually. So that's fine. So if we only have a vertex, then we just return WB, and we're not done, because we need to then create a context graph with C and FA. Maybe vertex FA. Oh, right. Yeah, no, that sounds right, because we do have an A inside a vertex. It is actually of type A, isn't it? Graph. Oh, we'll need to modify the type of the context as well. Yeah. So I'm not sure how we do that. I think maybe it's only applying it to the vertex. How does that work? C.vertex. It's kind of a lens, right? But I think we can do that with this notation. FA. Or F underscore. What's this? Yeah, no, I can't do that. I think there is a Purescript record modify. There is a syntax for that. Update using an underscore in place of the record to be updated. Yeah, C.vertex. Maybe I need to oh no, that's just a type synonym, so C.vertex should have the right type. Why wouldn't it have the right type? Using T2. Is it because I then need to change, because now I'm changing the type, and so I actually need to change the type of the inputs? That's true. Well, hold on one second. How does it work here? I did this refocus. I got the note from the context, and then I refocused. Right. Yeah, probably. Yeah, probably exactly for that reason. That otherwise I'd have to recreate the. I have to recreate each of the incoming edges and outgoing edges, but I can't do that. Whereas refocus, going to give me the correct type if I use it for K. But I think I have a refocus, right? Pretty sure I have a refocus. Can I use it here? I suppose I probably can, but it's only for focus graph. So do I need to write one here for a context graph? There's a recall focus prime right there. It's exactly awaiting us for this, I think. And indeed, right, those seem very inefficient. It ignores the A, ignores the focus of the context graph which makes sense. Then passes on to the focus, and so okay. So I create a context graph with C, and I refocus it. On FA. How strange. Oh. Holy moly. Oh no. F is W to B. Ah, that's bad. Rookie's mistake. Okay, so of course then this is all wrong. So let's rethink this. Yeah. So what we can do, given that we've reached a vertex and that we have our A, well, I mean, really one of the things that we can do is to call this G, and we can apply F to G. That will give us a B, right? Then we need to wrap that B. And so for that, we do need to do the refocus FG. No, FG might not give us the vertex we want to be focused on here. Or no, it does. It does. And so therefore we can create a context graph here with a, yeah, we can create it with a C, but we need, no, but we have refocused. So what's the deal with that? Well, we just need to, again, apply it like so. But then our types are not right. So maybe because of the C here. Good context. Context extracts the context. Is it this C that's really causing us trouble? Refocus is gives us a maybe. So yeah, maybe context graph. So we are close. I was trying with duplicate, and I had lined up to be using fold G for some reason. I wonder whether that's actually worth taking a look at, because yeah, apparently, yeah, you know what? I think maybe I'm going in the wrong direction here. And again, I need to remember what that is, and I think it's mapf duplicate. Given that duplicate is this. Okay. And then we need some way to write these functions, and that's what I was in the process of doing, I think. So let's try. Right, vertex. If we make a context from input, a vertex, and an output, input, a vertex, isn't, yeah, 4G takes something, it takes a B. No, it doesn't. It takes A to B right away. A to B, B to B to B, because the 4G is the new one. It's the one for non-empty graphs. So we do get the A to B here, and therefore that gives us the A we want, and that's the A to context G. That's what we want. Okay, and so overlay and connect. Are going to be B to B to B. So, well, they need to be context A to context A to context A, and same here. And that's AB. And what was the idea here? The idea is to create a context graph of context graphs. And the FGs are going to be context graphs themselves. And so FGs will have as vertices. It is not simple, actually. I wonder whether extend isn't simpler. So I was thinking GG could take an A to a context graph. Okay, I'm now thinking, if I don't do this sort of cutting in the direction of the grain of this data type, then I'm not doing it correctly. Doing it with 4G seems like that would be one of the ways to cut in the direction of the grain. But Here, given a graph, I would create a context graph of context graphs. I mean, I am cutting across the grain already because the whole foci thing is a little bit wonky already, I think. The fact that we pass through this focus data type to refocus, it's an attempt to recover some of the FGL things, but it does cut against the grain. And maybe there's nothing to do about this with alga. I'll take a small break here. Hey. Yeah, so I think this idea of whether I'm cutting across the grain or following the grain is actually pretty important here. And it makes me realize that actually this p-graph structure, this idea of a pointed graph that points that way, is actually, that seems pretty native to that representation. Although it's that's the simpler instance. It doesn't need any context. But maybe that doesn't matter. Okay, I suppose I should ask myself whether it's possible to, if I extracted a focus graph, then I could just get the context by asking context on the extract, right? That would give me the context. it will give me all the inputs and outputs that I want. So do I really have a reason to move about with this representation? Sounds like it's very not Alga native. Therefore, hello pointed graphs. And hello focus graphs. This I think we might want to forget. This, what was this? Class list. Something with that classes, I think, but I don't remember what that was. Okay. Okay. So do we call this a pointed graph, and do we try to? No, I think maybe we just try to rewrite this for pointed graphs. Define like so. I mean, I think this is really close to where we want, and maybe there isn't much more to want from that representation. But I get the feeling that maybe with pointed graph being represented like this, we're going to be able to sort of swap things in order to move the focus where we want to move it. And I don't know if that's going to allow us to follow edges or not, but it might. So that's quite an interesting thought. And that means I'm probably going to call you prime. Oh, I'm not even using you here. Okay, so let's go for pointed graphs and give that a shot. Let's derive our normal things, and we don't need to name instances. Let's try this. And okay, yeah, I don't know that I want to even think about it that way here. I think I'll start more from scratch. And actually starting with extract here is a pretty interesting one, because if we have the p vertex n, then it's n. and then maybe we case on PG. Oh, yeah, no, it's just P vertex. And if we P connect P N, then we have to extract P. And we can ignore this. That's really simple, actually. I think. Yeah, I mean, maybe we don't want to call extract. Maybe we want to do an inner loop here. Maybe you want to do an inner loop where go PG go P. Ah, we can do this, I think. Yeah. And duplicate. If we wanted to duplicate a P vertex N, we just put a P vertex N inside. And oh, we need the P overlay as well here, I'm pretty sure. Yeah. And so what do we do if we have a P connect? Well, on the left-hand side, we want the P connect. We have a P connect PQ. And so we would P connect PQ here, and we just pass like a connect PQ here for the regular graph. I think so. Overlay. And P overlay and overlay. And the really pointed graph. And yes, P connect, P is a pointed graph. So there's probably something smart to do if we were lazy here. Which would allow to do the amortization for lazy persistent data structures. But here, I suppose we need to convert that P into a regular graph. And that's really long. But I suppose that's part of It's interesting. It made me think that maybe we could carry that pointer as a kind of a bit like in a finger tree, or like these skew structure, like these kind of counting structures. Could we have yeah, I don't think that would help. I mean, maybe it would, but first of all, I think I'm thinking about it would, like the way that I'm thinking about it right now is more like dependently typed. So it wouldn't be so simple. Meaning the left-hand side would be somehow annotated with a P, whereas the right-hand side would be annotated with a G or something. So the pointed bit would be on that left side, the non-pointing bit, the regular bit would be there, but that would give us some homogeneity. I don't think we can do that here, because that would be mixing types and type parameters. I think I'm doing a GDT again here. And this, it would not be about existentials this time, but about type equality. Maybe I should try this in Haskell first. Because otherwise, I simply have to have a graph to pointed graph function, right? To graph. Mostly pointed graph to graph. And that it would be fairly, I mean, it would be super easy to write. That's not the problem, right? Well, so let's write it for now. see if we can get our types to line up. Because here we're saying you'll have a two graph P. And we don't need to have a two graph Q. And extract wouldn't be of the right type. That's strange. Oh yeah, okay. Like that. And yeah. To graph P. Like that, we need to be recursive. And yeah, and then well. How would that not work? P-connect, we wrap it, we say fairly arbitrarily. And we try to put yeah, I think that makes no sense actually. Let's say we have two nodes with one edge. We've done that example before. So we would be connecting, instead of connecting true and false, we'd be connecting the graph that's focused on true on the left. Okay, I'm a bit confused with types here. Because if pconnect takes a pointed graph of n, when I pass it to pconnect, it's not clear that I'm making, whether I'm actually making another pointed graph or whether I'm duplicating. Basically, yeah, a pointed graph of a pointed graph for connects and overlays seems like it will be a pointed graph. It's just when you reach the end that it's not clear. Okay, I'm confused. Let me just try a thing. If I say this, no, on this type check, I want to make sure. Okay, yes. Yes, that's annoying. We don't always have an n. So we can't test that. I have a pconnect PQ. It's an edge. Between subgraph P and Q. Okay, maybe I need to put type annotations here because this is a pointed graph A. And this is a graph A. Yeah, and so if I take a pconnect of that, then I get a pointed graph of, just a pointed graph of n again. Not a pointed graph of n. And that you can't believe me because pconnect PQ is a pointed graph of A. So do I have to? But you don't even wanna. Yeah, I am confused here. How would I think I need to build one. I need to build an example of a graph of graphs. Pointed graph of pointed graph of Boolean and a p vertex of p vertex of true should be one of those, right? Yes. However, what about a pconnect of p vertex of false? That's just a pointed graph. No, well, hold on, we want a graph here, okay. But yeah, then that's just a pointed graph of Boolean, right? So fine, we can pconnect this with a, well, it would be a graph, so a connect of vertex true vertex false. But then you're saying that's also a pointed graph Boolean. And I would agree. So then what is a pointed graph of a pointed graph Boolean? Oh, I need to wrap those in p vertices. Yes. And yeah, these two. No, this. What does this need to be wrapped into? Just a regular vertex? I think so, actually. That's a bit weird, but. Match graph with pointed graph. Pconnect. I'm going to take that p vertex, which is a pointed graph, and we want a graph of pointed graphs. So a vertex of pconnect, and in that case, it's going to be p vertex here and vertex true. Yes, I see. Okay. So we're on our way, but I'm going to stop here. I think this is a good place to stop. I think I've started to make sense of what's happening here. And I'm going to leave the next step to later. Maybe do it like so. Yes, perfect. So I just need to wrap those things in vertices. I mean, is it justified? Yeah, I think it is. I think I'm going to be able to disentangle that, or at least that's where we're at, right? So it turns out that in fact we are not doing the context graph. So let's see. Turns out context graphs might be a bad idea in Arga. So therefore, we started on Comonad for pointed graphs, but as via Paolo. And we have done that. So next time we'll continue on Comonad for pointed graph. Great. And that's it for tonight. Thanks a lot for watching, and see you on Thursday. Bye-bye.